Welcome, everybody. I hope everybody's doing well. Today, we have the pleasure of hearing from Sanjeev Raja, who's going to be talking about his paper, whose title is shared right now: Action-Minimization meets generative modeling, efficient transition path sampling with the Onsager-Machlup functional. So, with that, Sanjeev, I'll pass it over to you.
All right, thanks so much, Ezra. I appreciate it. And always nice to present in this reading group. This is, I think, my third time now presenting here, so it's always a great community. I've always had some good interactions, so looking forward to this. So yeah, hi everyone. I'm Sanjeev. Just completed my third year of my PhD at UC Berkeley in the Berkeley AI Research Lab, and generally work on machine learning for atomistic simulations, molecular simulations, recently generative modeling and sampling. So today I'll be talking a little bit about a recent ICML paper, which is tackling the problem of transition path sampling through the lens of generative modeling. And so I'll try to keep an eye on the chat for questions as I go, but depending on how things unfold, it might also be easier to answer some at the end, but I'll just sort of keep track of that as I go on. So feel free to put questions in the chat.
Yeah, I'll also take a look at the chat. So if anything comes up, I can let you know. That way, you
Yeah,
don't have to keep checking.
feel free to stop me and ask me to answer something if you think it'd be pertinent. Yeah, cool. Yeah, okay. So broadly speaking, this talk is going to be about transition path sampling, which is a sort of a important canonical problem in the field of statistical mechanics, and sampling like potential energy surfaces of systems in general. And so I'll give both a bit of a theoretical background, but then also try to tie this to practical applications as much as possible. So um, as many of you probably know, a lot of atomistic systems that we care about, whether it's proteins or materials or small molecules, exist in an ensemble of states. So there's an underlying potential energy landscape at constant temperature. This is like a Boltzmann distribution, and the goal is to sort of sample from this very complicated energy landscape, so that we can sort of access interesting or important events that may inform our understanding of these systems or help us, for example, design new materials, molecules, etc. And so, yeah, learning and sampling from these distributions is sort of a foundational problem with a lot of different applications. And sampling is hard for a lot of reasons. So first of all, computing this energy function in the first place, if you want to sample from a distribution, you at least need to compute the unnormalized like log densities, which are energies. And even computing these energies exactly can be difficult. So these potentials are often based on methods like density functional theory or quantum mechanics, like solving the Schrodinger equation precisely. And doing this is pretty prohibitive for large systems that we care about, like proteins and materials and things like that. And so we typically need some sort of approximation to the energy function. These days, the hot topic is machine learning force fields as sort of a surrogate model for these energy functions. But even if you had like a fast energy function, you inherently just have long time scales in molecular dynamics. So for example, molecular dynamics is one way to access these time scales. Like if you consider like a protein folding event, these events maybe occur on the time scales of microseconds to milliseconds or even seconds. But the best ways we know how to sample are things based on molecular dynamic simulations. And we often need to take like very, very small time steps in these simulations to maintain numerical stability. So clearly there's like a huge separation of timescales here. And this is a very, very challenging problem that people have known about for decades. So this is nothing new that I'm saying here. So again, a fundamental challenge is that we can, even if we could make like each step of an MD simulation faster using really promising techniques like ML force fields and others, we still have to take like many, many time steps to observe interesting or rare events like a protein going from an unbound to a bound state, or maybe a ligand binding to a protein or something like that. And so a new way to sample that's sort of gained traction in recent years is based on generative modeling. So instead of directly learning the energies and the forces, could we directly learn how to sample from the underlying Boltzmann distribution? So this is gaining a lot of traction. This is a very promising research area. I'm sure many of you have heard of models like BioEmu, which essentially kind of tackle this, or Boltzmann generators, which was sort of an early version of that line of work, which is basically trying to sample from the equilibrium, like Boltzmann distribution of high dimensional molecular systems, usually via supervision from like a large data set of samples. Although there's also now work on trying to sample even without samples, without data samples. So this is sort of a new direction that people have really been seeing some interesting results from in the last few years. Um, and so, yeah, basically the idea in a generative modeling paradigm is given a probability density function, you want to sort of map an easy to sample from distribution, such as a isotropic normal, to a complicated distribution, in this case, the Boltzmann distribution. And so there's no like explicit energies or forces that you're sort of regressing to here. You're just trying to learn the distribution through samples. And so, as I mentioned, this is a very active area of research. There's probably the most high-profile recent one that model in this sort of vein that came out was BioEmu from the Microsoft team. But there's also, a lot of models that are starting to do this. Most of them are based on the popular diffusion or flow matching paradigms. And so if we go back to our like sort of foundational problems, where do generative models help in sampling from these distributions? They certainly help with the first principles energy calculation side of things because, well, there is no energy evaluation in a generative model. You just sample from the model, so that's nice. But this idea of having long timescales sort of is still an issue. So um, in some sense, generative models help with the long timescale problem because you don't have to iteratively traverse a sequence of states to let's say, go from one energy well to another. But it's still the case that like rare or transition events might still be hard to sample. So if you just if these rare events are not really present in the data set that was used to train a generative model, it's likely that it would still be hard to sample or like see these kinds of rare events. Um, and so a canonical problem a canonical sort of problem that sort of exemplifies this is that of transition path sampling. So many of you might be familiar with this problem, but given two metastable states of a molecular system, so for example, the unfolded and the folded states of a protein, the idea is we want to sort of sample plausible transition pathways connecting them. This is a problem that's been studied for decades. This is certainly very, very well studied problem. And again, it's the same exact problem where you have large energy barriers support dividing your states. And so transitions between them are rare and occur on pretty long timescales. So on the order of microseconds to milliseconds for like many systems. So this is sort of beyond the tractability limit for like an unbiased or naive MD simulations. You would rarely, or if ever, sort of sample the transition paths using a method like this, using a method like unbiased MD. And so the question we asked in this work is, given that generative models are becoming increasingly a popular and promising approach for sampling from high dimensional atomistic systems, could there be a way to repurpose these atomistic generative models to generate hypotheses for transition path sampling in sort of a minimal or almost like zero shot way? So given that we have these increasingly good models that are trained on a lot of data and sort of have good representations of atomistic systems, is there a way we can leverage those good representations to tackle this important problem? And yeah, so if we could do this, we could leverage sort of the scalability of generative model training and also the increasing availability of large structural databases. So of course, there's the PDB, which is crystal structures, but you also have now like MD datasets, things like Atlas, MD-Cath, there's a Misato dataset, things like that. So the vision is, if we could leverage sort of large scale data, then we could solve this problem much better than it was done before, because existing sort of methods for this problem of transition path sampling are sort of very bespoke for each atomistic system. So, there's methods like based on sort of using reinforcement learning or learning a bias potential to bias the system from one state to another. There's a whole line of machine learning work that tackles that. I won't discuss that in depth in this talk, but in our paper, we provide a review of those methods if you're interested. But what's in sort of common with all those methods is that they sort of need to be retrained for every new atomistic system of interest. And so there's very little reuse or very little to none of reuse of like representations that you learned for a previous system on a new system. And so we sort of want to change that state of affairs by using these general purpose, uh, well-trained generative models in a zero-shot fashion if possible. And so a preview of our approach is to sort of leverage the connection between a certain class of generative models, which are in this case score-based generative models. So we consider denoising diffusion to be sort of the canonical example of a score-based generative model, but flow matching can also roughly be fit into this framework. Even though it's not exactly doing score matching, you can extract a score from a flow matching model. And we basically show that the learned score function of a score-based generative model like diffusion or flow matching induces a set of dynamics on the data manifold on which it was trained, such that if you minimize a quantity called the Onsager-Machlup action, you can find high likelihood paths between arbitrary points on the data manifold on which the model was trained. And so I know that's a sort of a lot, and we'll break that down step by step. But the high level idea to take away is sort of blending these ideas from statistical mechanics based on action minimization with large scale, hopefully well trained generative models. So just to give some preliminaries, we generally want to consider sort of stochastic differential equations as our sort of generative hypothesis for how paths are generated in transition path sampling. So typically you have some, this is like a very simple general SDE, where you have a drift term, which in the case of transition path sampling is like the negative gradient of an energy. And then you have some physical constants, but then you have sort of a Brownian motion term that models interactions between the system and a heat bath. And so in transition path sampling, we want to find paths which have maximum probability under this SDE, given some fixed endpoints. So you have some starting region A and some ending region B, and you have sort of 2 points sampled from these endpoints. So this could be, for example, the unfolded and the folded state of a protein, or like the products and reactants of a chemical reaction, or something of that nature. So this is the general goal. And it turns out that from classical results in statistical mechanics, just based on um, solving the Fokker-Planck equation for this SDE, um, the probability of any like particular path, x, drawn from this SDE is actually given by a Boltzmann-like distribution, where instead of sort of your traditional energy function, now you sort of have an energy function over paths. And it turns out that this function over paths, or a functional, is called the Onsager-Machlup action. And it turns out that you can think of this as like a path energy. So the higher the energy, the exponentially less likely you are to observe this path when you realize this stochastic differential equation. So what is this? What is this S? What is this Onsager-Machlup action? So in practice, of course, on a computer, we have to simulate discretized paths from an SDE. So if we consider a discretized path of length L, the Onsager-Machlup action is actually a very intuitive decomposition of 3 terms. So you have this A, B, and C term. The A term essentially enforces that subsequent points on the path are somewhat close to each other. So this is just penalizing a pairwise distance norm between points. If you were to just optimize this one term, you would essentially get a linear interpolation. That would be like your geodesic of just minimizing distance. But of course, a linear interpolation, as anyone who has looked at any of these interpolations before, you know that a linear interpolation would give you all sorts of, bond collisions and things like that, steric clashes. And so there's another term that basically encourages the path to lie in regions of the potential energy surface with a low force norm. So remember from the SDE that this symbol here corresponded to the drift. So in the context of molecular simulations, this is a force field. And so you want to basically be in regions of chemical space where your dynamics are stable, such that you have a low force norm. And then finally, this last term is a little bit less important. We don't really use it that much in our experiments, but this is sort of entropic correction term, which accounts for the curvature of the potential energy surface, and it incorporates temperature effects. If anyone's interested in the details of that, I'm happy to discuss that more, but in the interest of time, the focus should be on these first two terms, which sort of provide an intuitive decomposition of like what you would want to look for in a high likelihood path. And so this is sort of the preliminaries for transition path sampling. And now let's connect this to generative models. So this so far seems kind of removed from the generative modeling paradigm, but I'll now show how we can connect this to the class of generative models that hopefully many of us are familiar with. So again, I'm sure many of you are familiar with diffusion models, but just very briefly, the idea is to formulate a generative process as sort of a Markov chain between data and noise. So on one hand, you have a noise distribution. On the other hand, you have a data distribution. And the goal is that, it's easy to transform from data to noise, but to go from noise to data is, of course, generative modeling. And so you want to learn essentially a model which learns how to denoise to sort of move in the left direction on this Markov chain. And it turns out that DDPM is the objective is reduces to like score matching at multiple scales. So at each level of this diffusion process, the optimal score function that's learned, the optimal sort of, denoising model here, this epsilon theta, is related via a simple, just like up to a scalar, to the true score of each marginal distribution at each time level. So at each time of the diffusion process, if the model is perfectly trained, it has learned the score or the gradient of the log density of each sample. And so then you can think of sampling as sort of this gradient ascent procedure on the probability density. And flow matching is sort of another paradigm from which a score can also be extracted, where you're just sort of changing the probability path. So your path is no longer sort of this variance preserving SDE, but it's just usually like a simple linear interpolation. And the regression target is, instead of learning a score, or instead of learning a denoiser, you learn sort of a velocity field. But it turns out that under some mild assumptions, which hold in our cases, you can actually extract a score function, a score estimate from a flow matching model as well, even though it's not explicitly performing score matching. So the takeaway here is that both diffusion and flow matching sort of enable extracting a score function. Okay, so now let's put this all together. So we've introduced generative models from which you can get a score. We've introduced the idea of transition path sampling, and we've introduced the idea of the Onsager-Machlup action. So how do these all connect? So it turns out that like through the lens of generative modeling, transition path sampling can almost be thought of as finding high likelihood interpolation paths between arbitrary points on a data manifold. So interpolation is sort of like a thing that people in the generative modeling world have kind of done from the beginning. Like in the early days, even with VAEs, people would encode the samples and then do a linear interpolation in the latent space and then decode that and show that that sort of corresponded to some semantically meaningful interpolation in the ambient data space. So similarly, we sort of employ a similar idea here, except we don't do a linear interpolation. We do something a little bit more clever. So the idea is, if we want to use the OM action or these concepts from transition path sampling, we need to like construct an SDE of the form that I described before that has something to do with the generative model. So far, this equation here has like no connection to a generative model, but we want to formulate a connection such that paths under this SDE would have high likelihood under the data distribution. And so what we can do is introduce sort of a mathematical model for like, if we want to find high likelihood paths connecting 2 points on a data manifold, we sort of need like a hypothesis class for how could these paths have been generated. And hopefully that hypothesis class is an SDE of this form. So think about as just a conceptual model, the process of repeated one-step noising and denoising with a diffusion model, or more generally like a score-based generative model. So what you would do is maybe you have a data point and you add one step of noise to it using the diffusion model's forward diffusion process. And then you just denoise it using the diffusion model's learned score function. So you just do noising. Oh, I'm sorry. I think these might have been flipped actually. The first one is denoise and the second one is noise. I apologize for that. So the first one is denoising it such that you use the score function essentially to move closer to the data manifold, and then finally you noise it to add noise. So intuitively, what this does is it balances sort of the maximum likelihood or likelihood maximizing properties of following the score function with the stochasticity of the noising process. And it turns out that if you put together if you like sort of combine these two updates and take the limit continuous in time, um, you actually get the following SDE. So you get this is essentially a stochastic process, which just amounts to doing basically an SDE using the score function of the learned generative model. So if you were to basically like produce a path by just repeatedly doing this process, it's essentially like kind of doing Langevin dynamics, um, just with the score function of your generative model at whatever time in the diffusion process you want to do it at. So um, this is essentially a hypothesis class for how are paths in a generative model formulated. And so now that we have this hypothesis class, essentially we can conclude that generative models induce a set of stochastic dynamics within every time step of a generative process. Via its learned score function. So we all know about the stochastic dynamics from noise to data, but that's across time levels. Whereas this is a stochastic dynamics within a given time step of a generative process. So like how would basically like a random walk within a given time level, let's say t equals 123 of the diffusion model look like? And so we sort of have now a conceptual, a mathematical model for what that generative process looks like. And so now
So
that we
here
have a
you,
generative,
or sorry,
yeah, go ahead.
can I just
Yeah,
jump in real quick?
yeah,
So you guys kind of you formulated this noise and denoise thing, and then you show that in this limit you get Langevin dynamics. But I'm just curious why you guys framed it like why you framed the derivation in this direction rather than saying, um, my understanding is a lot of the TPS stuff is the application is in molecular dynamics, where the dynamics you care about are like some form of Langevin dynamics like this.
yeah,
So as opposed to saying this is like, as opposed to trying to kind of reverse engineer the dynamics, uh, you could imagine an alternative where you say we want to end up with these dynamics, and as it turns out, this noise denoise thing in the limit actually yields this thing. But you guys kind of framed it in a more general way, so I'm sort of curious if there are like other dynamics that you guys like. I guess you could consider transition path sampling for other dynamics, but uh, yeah, I'm just curious because it seems like it
yeah.
suggests that there are other
That's
things to consider.
yeah, that's a great question. So you're right that in this case, of course, Langevin dynamics is the physically like motivated dynamics that we actually want to recover. But we sort of wanted to keep this at the beginning. We wanted to keep it broader and just think about interpolations or like paths between arbitrary data, between like two data points on any data manifold. So whether it's a data manifold that comes from molecular dynamics, in which case it's a Boltzmann distribution, and this is literally Langevin dynamics, or any other data distribution. Like it could be also the data distribution of a non-exhaustively sampled Boltzmann distribution, which is typically what we have in practice, or like images or something like that. In that case, it's no longer like actual physical Langevin dynamics, but this analysis sort of still holds in that case. So we just sort of wanted to keep it a bit more general to admit, at least in the theoretical setup, arbitrary data modalities. And we are actually working on some follow-ups to this work that actually do explore those additional data modalities. So stay tuned for that. But that's sort of was the motivation. Does that kind of make sense?
Gotcha. Yeah, it does.
Yeah, yeah. Okay. Right. So the key takeaway right here is that we have now a set of stochastic dynamics. And so interpolations, or in this case, transition paths, can be thought of just as realizations of the stochastic differential equation induced by the generative model. So now we've established a clear connection between generative models and the sort of transition path sampling like SDE. And so the final piece in the puzzle is that we just need to connect this to the Onsager-Machlup action. And so it turns out that if we interpret transition paths as being drawn from this SDE, then we can just maximize the probability of paths by minimizing the Onsager-Machlup action under this, using this score function as the new drift term. And so essentially the thing that we minimize is this action, which is the action induced by a pre-trained generative model. And so all that is again the sum of the same three terms that I had discussed before. You have your pairwise sort of distance term, your path term. You have your drift or force norm term, which is now being replaced by the score function at some time level. And then you have a force divergence term, which again is a little bit less important and also a bit expensive to compute. So because of this divergence of a score function. So we have some tricks in the paper of how to compute that using Hutchinson's, but we don't generally use it too much. But I'm happy to discuss details of it if anyone's interested. And so again, so far, this is general for any data distribution. But like kind of going to what Ezra asked, if we have specifically have a Boltzmann distributed data distribution, then this has the additional sort of interpretation as like a force field minimization problem. So if we assume like an energy-based model for our data, then the learned score function of like a score-based generative model can be interpreted as a force field, right? Because the gradient of the log of this distribution is like negative grad of u up to constants. So you can think of a diffusion model or a flow matching model as actually like at time equals 0 at the data distribution of actually learning like a force field, which folks in this 2-for-1 paper have pointed out and used. And so this is, of course, actually true. This energy-based model is actually true for like molecular data sets at a constant temperature. So under that sort of interpretation, the score-based generative models are like unsupervised sort of force field estimators. And then this OM action is like reduces to like a literal, like this whole analysis reduces to like literal over damped Langevin dynamics. And then we're just performing like transition path sampling by minimizing the OM action using the diffusion model as a force field. And this idea of using the OM action to do TPS is not new. We did not invent that. That's been also around. But under this basically interpretation, we're basically just swapping in the diffusion model as a force field. But in a general sort of setting, this is applicable at any sort of time level of the diffusion process. So what we sort of gain on top of existing methods is that we have a sort of time continuous, or we have a set of score functions at different latent times from like t equals 0 all the way to the noise distribution. And so we can sort of, as you'll see, we can control the diversity and the qualitative properties of our path by varying at what latent time or what sort of noise level of the diffusion process that we do this interpolation at.
So if you did do it at like just like some really noisy level, and then like if you found a really good transition path at like some really noisy marginal, and then you transported it back to 0,
Yeah,
is there anything you can say about that path, or is there any reason
that's a
to
good,
like
yeah,
that you
that's a good
couldn't have a
question.
situation where all of a sudden that's like a really low probability transition path?
Yeah, exactly. That's a good question. So, as you get closer to data, sorry, as you get further from data, like if you just do interpolation at like a very deep, noisy like level, and then you map it back, you do the optimization, and then you map it back. Like the mapping back process essentially will like erase everything that you did um, in the optimization, because like the idea is that like in the extreme limit, if you were to do interpolation in the pure Gaussian level, and then you were to decode, all the information would be lost because you're still just doing IID sampling at that point. But basically, what we do is sort of find like an intermediate, something close to the data distribution to do this at, such that when we denoise, we still get reasonable paths. But yes, it is true that when you do the optimization, you can only really say something about the level of level of the diffusion process at which you did the optimization, not the data distribution which you decode it back to. So there's a couple of variants of our approach that we sort of explore to where we actually sort of still do the optimization in the data space itself. So sort of just treating the diffusion model as a force field. That's really what we focus on. But yeah, the idea of the denoise noise SDE is you can only really say something about the likelihood at that marginal time level. Yeah.
Cool.
Yeah. So basically, then our procedure sort of reduces to a very simple sort of conceptual model, which is we literally just want to find paths which minimize the action induced by our model. So we have some action. We have some pre-trained generative model that's trained to basically just produce IID conformations, and the goal is to just use gradient descent over, let's say, the path to find the path which minimizes this action. And so importantly, what we'll do is we'll keep the endpoints of the path fixed. So we'll basically just manually kind of zero out the gradients of the endpoints because this is a transition path sampling, so we want to keep the endpoints fixed. And then just do sort of a gradient descent procedure over the whole path while keeping the model frozen the entire time. That's the key. So like I mentioned, we can sort of control the diversity of the paths by doing the optimization at various levels of the noise hierarchy, which I'll demonstrate. So the basic idea is just to take show an algorithmic perspective. You choose some optimization time. So like for example, the if you want to use a slightly noisier version of the force field, which empirically actually sometimes correlates better with the true forces, you pick that, and then you have a generative model with the corresponding score function, and you have sort of two atomistic configurations which you want to interpolate between. You compute the initial guess, an initial guess path, which essentially amounts to sort of doing like a noising the endpoints, linearly interpolating, and then denoising. This sort of gives you a good initial guess to start with. And the T initial that you choose sort of controls the diversity of the initial guesses. So if you choose a larger T initial, you'll have more diverse initial guesses. And if you choose a smaller T initial, you'll have less diverse initial guesses. You can look at the paper for the details. And then essentially you just do gradient descent. So you compute the OM action using the learned vector field, using that equation over here that I showed, this one right here. And then once you compute the action, you just optimize it using gradient descent with sometimes with momentum or sometimes not actually. Sometimes it helps to just do pure SGD. And you just manually zero out the gradients at either end. And so what you get with this is just a very simple procedure that allows you to find sort of high likelihood paths using a generative model. And so I'll now dive into just showing a teaser of some of the results that we had. But I guess this could be a good point to pause for questions. Okay, could you explain a little bit on equation 14? Yeah, so as I mentioned, so equation 14, that's the equation 14 in the paper, which here is not labeled as such, but it's just this equation right here, this one right here. This is just the Onsager-Machlup action induced by the generative model. So it's the exact same thing as the OM action I introduced before in the abstract sense, where you have basically you have three contributions to it. You have sort of a path term, which says, okay, I have like points along my path, and I basically want smooth transitions along my path. I want sort of the points to sort of vary smoothly and not have huge jumps. And so just minimizing this would give you a linear interpolation. So of course you don't just want that. You also want to remain in regions of low force norm. But in this case, we're replacing the force or the drift with the score function of the generative model. So we want to be in regions that have sort of low force norm. And then finally, this third term has to do with some entropic contributions. So like you want to be in regions with sort of like lower curvature of the potential energy surface, because regions of like very high, like very concave regions are very unstable. So there's actually some, depending on the form of the SDE, if you use like the Ito or Stratanovich convention, this term actually disappears, which is why we don't sort of emphasize it too much in the paper. But yeah, so these are essentially the two terms. And intuitively, you can think of these physical constants as sort of, you can think of these physical constants as sort of controlling the sort of level or the relative contributions of these terms. So for example, at large time steps, like if you assume that you want to do transition path sampling at a large delta t, then this path term is downweighted because at large delta t's, like larger pairwise distances are permissible. Um, so you would basically, when you increase delta t, you would downweight the path term. Whereas if you're taking very, very small time steps, then you're going to upweight this path term because, if you're taking very small time steps, you better have points that are very close to each other. And there's similar sort of explanations for these other terms here. Um, how is the method sensitive to the number of discretization steps? That's a great question. So um, again, you can think of this as that it's more sensitive to the like in some sense it's sensitive to like the total time horizon of the optimization. So the total time horizon of the transition path sampling is given by like L times delta t, right? So each step it has a spacing of delta t, and then there's L steps. And so basically what you want to do is you have a total time horizon of like L times delta t. And so I guess your question is like, for a fixed time horizon, for a fixed L times delta t, what happens if you like increase the number of discretization steps and then like reduce the delta t commensurately? And so I guess my empirical answer is that yeah, if you set it's this sort of the same thing as like with molecular simulations. Like if you set delta t too large and use too few path points, you will not have the correct resolution, and you'll sort of like you might jump to sort of you might hit the right regions of your transition path, but you won't have the resolution necessary to do so. And sometimes actually optimization fails. But as you increase L and decrease delta t commensurately, you sort of just see smoother paths and smoother transitions. And so in principle, or sorry, in practice, we tend to use like anywhere between like 100 to 300 um, sort of discrete waypoints. So like L equals 100 to 300 for the sort of small proteins that we consider in our paper. It's likely that for larger systems, you might need to go higher. But the method scales like linearly in terms of compute cost, linearly with L, because you need to compute sort of this is the dominant thing that takes up most of the cost, is computing gradients through this term, and you have to do it L times. Yeah. What is the tau here? Is it the time step corresponding to each xi? So the time step corresponding to the differences between the xi is not tau. It's given by this delta t. But tau refers to the diffusion time step. So I apologize if on a previous slide I used t to actually I definitely did this, so I apologize. Like used t for the diffusion time, but in this case, tau has to do with the diffusion time. So what point in the diffusion process you're taking the score from? Because in a diffusion model, of course, you have or a score-based generative model, you don't have just one score function, but you have like sort of a continuous in time score function, which is like, I guess, approximated via like discrete times. So this is really like which time level you're choosing. So tau is the diffusion time and t is the sort of physical time. Hopefully that answers your question. How important is it that the distance between points is uniform? Um, that's a good question. I guess it's just the fact that if your distance between points is not uniform, you would also just need to like pass in that spacing, right? Like here, you have to have a delta t sub I, just based on the spacing, and then I think the math is all fine if you do that. So we haven't tried that, but I think that as long as you like, if you have a hypothesis that some points are closer to each other than others, or if you want to sort of like allocate more points to the transition region, you would just have to change the delta t accordingly in those regions. I'm going to move on in the interest of time, but I think I, at least at a surface level, got to all of your questions. So happy to chat more later if necessary. So, okay. So yeah, just going to show sort of some results. So a very like toy playground is like a Muller-Brown potential. So imagine this is a sort of a 2D sort of system, which has basically like three energy wells separated by barriers. And so imagine we like, for this very like toy example, we have like a generative model that generates samples that look like this. So it doesn't really sample the transition regions that well. But the idea is that using our basically OM action procedure, you can basically sample transition paths where sort of this yellow corresponds to sort of the initial linear interpolation guess. And then the sort of purple with the red samples corresponds to the final path you get after OM optimization. And this is doing this at various sort of levels of latent mixing, where you sort of do the OM optimization at different times in the diffusion process, and then you decode at the end. And what we see is that like the total diffusion process has, I think, 256 steps in this case. That's the discretization, but we vary it from 0 to 40. So in the case of t equals 0, you're basically just doing interpolation in the data space. And so there's no diversity around your path, but you capture the transition path well. In the case of, as you increase sort of the time at which you do the latent mixing, you basically get the correct path still, but you also get some diversity around the path that just has to do with the natural diversity of the diffusion process of the generative process of a diffusion model. And eventually, kind of this is similar to Ezra's question, like if you kind of go too far, eventually when you decode back to the data space, you sort of lose the correspondence with the endpoints that you specified for the OM optimization. You'll also start, if you notice, it might be a little hard to see here, but you start sampling stuff in this energy well. Basically, you start to ignore the conditioning given by the two endpoints. And in the limit that you went all the way to t equals 256, which is the maximum diffusion time here, you would just get IID samples. You would have nothing to do with transition path sampling. So this is sort of a knob that you can tune to get sort of control the diversity of the samples.
Just to
And
play
so
devil's advocate, or
yeah,
sorry,
yeah,
you know what?
yeah.
I'll ask after this slide because I think it's connected to it's the same Muller-Brown thing.
Sure, sure. Yeah, so another thing we can do is basically, as I mentioned with that forced divergence term, which I said was not to worry about too much, but we did sort of consider it in the context of Muller-Brown, is you can sort of modulate the sort of temperature of the transition path sampling using this sort of Hessian or like divergence term. So here it's written as a D, which is diffusion, but there's like a simple relation, this like Stokes-Einstein relation that relates between diffusion and temperature. So you can think of like increasing diffusivity here as analogous to increasing temperature. So at higher temperatures, if you use this basically, if you add this to the objective function of the OM action that you're optimizing, you essentially get paths which cross at higher energy barriers, which is sort of intuitive in the sense that when you have sort of a higher scale of thermal fluctuations, which is what higher temperature is, you sort of spend more time in the energy wells and then sort of shoot over higher energy barriers when you actually do make the transition. So this is sort of something that we sort of see in this toy example, that you can kind of control the temperature of the transition just by increasing this term. And so if you went too far out of distribution, of course, the generative model was trained in a certain distribution, and so there might not be super good support in this area, but this is sort of just to show that you can kind of simulate this higher temperature process in this fashion. Ezra, did you want to ask your question?
Oh yeah, I was going to ask just to play devil's advocate for the sake of discussion. To what extent is so I would imagine like one of the like largest potential problems is that you don't know that your diffusion model learns the transition region very well because it probably doesn't see any
Yeah,
samples there.
right.
So to what extent does the fact that you learn the path here, to what extent is that the model is sort of robust to not seeing samples in these transition regions, and that kind of even if it doesn't, the geometry is like easy enough that kind of the path will kind of kind of to the right thing if you kind of have a good enough first guess? Or to what extent is that like kind of in two dimensions, if you draw a line between the two modes that have been noised a little bit, you'll like roughly get the right path. I think in high
Yeah,
dimensions, it's like it's really hard to visualize to what extent like that would still hold. I'm just wondering if you have any intuition there.
yeah, that's a really good question. Actually, we explicitly did this experiment for some of the more complicated systems, like for the fast folding proteins, which I'll show in a second, where we
Oh,
basically
sweet.
starved
Okay. Awesome.
we started with a model of data in the transition regions, and I will show the result of that in a second. But to answer your question on a higher level, I think it is certainly a limitation that if your underlying data set does not sample the transition region adequately, um, like you're going to have problems because your distribution is not well defined there. So I think in those cases where you really truly cannot sample those regions very well, um, like the idea would probably be to use a combination of like methods using data, but then also like methods that have access to the ground truth energy function that can sort of guide sampling in the correct manner. So I think like the work on neural samplers and like existing ML methods for TPS assume access to the ground truth energy function, which I think is generally a fine assumption because you can just use like a classical force field or something for proteins. Um, and so in those cases, I think some sort of like bold approach using both data and a ground truth energy function would be important. Um,
Gotcha.
but yeah, so we also apply this on like some more difficult systems. So the fast folding proteins from the SHA are sort of like a very nice environment in which to test this because we sort of have the ground truth very long exhaustive simulations heroically done by them on the Anton supercomputer like over a decade ago. So we sort of have like a way to validate that our transition paths are correct by comparing them to the reference MD. Um, and so what we can kind of see as we sort of project our these proteins onto a sort of two-dimensional representation, as is commonly done in this sort of area. So we consider like the Tika coordinates, which are like the two slowest degrees of sort of slowest autocorrelation, like slowest sort of time degrees of freedom. Um, and so in general, right, we sort of define endpoints between states. So we define endpoints as our transition paths, and we ask the model to we assume we have pre-trained models for this, which we actually source from previous work, or in some cases train our own. Um, and essentially, we find that our transition paths, via a variety of metrics, like looking at the energy profile along them, as well as looking at correspondence to the true energy, to the true paths that you find in reference MD simulations, actually match pretty nicely. So you get transition paths which are fairly physical. And in the case of like the BBA protein, where there's sort of like uh, bimodality or heterogeneity in how the transition occurs, we can actually sort of capture like multiple ways in which that transition occurs, which is nice. Like so, we have diversity within the transition state ensemble, and like inspired by actually a paper that Hannes and Bowen wrote. We sort of used a similar sort of evaluation metric to sort of evaluate how these transition paths, like how good they are. So we use sort of this idea of Markov state model analysis, where we essentially sort of cluster this Tika space and then fit sort of a Markov state model and sort of see whether the paths that we produce, broadly speaking, have high likelihood under those Markov state models. And so we compute sort of a set of metrics, which again were heavily inspired, if not directly taken from Hans and Bowen's paper, which was generative modeling of MD trajectories. Highly recommend if you haven't read it to read that. Um, and so we essentially show that compared to like varying lengths of MD simulations, so from like anywhere from like 1 microsecond to 100 microseconds of MD, um, these transition paths that we find are like we will first of all like these lengths of MD simulation often don't even get any transitions, don't observe any transitions because transitions are rare. Um, but sort of our methods like consistently sort of find valid transition paths. And what do I mean by valid is just that they sort of have non-zero probability under this ground truth Markov state model, and that they're generally capturing a reasonable distribution of states that are visited by the true sort of sample. So they're sort of going through the correct regions of phase space on their way between sort of endpoint A and endpoint B.
So how
And
are you
yeah,
sampling the?
yeah, go ahead.
I was gonna, jump in and ask, how are you sampling the transition paths? Maybe this could totally be my kind of lack of context showing, but there's my understanding is that there's some transition matrix between modes.
Yeah,
So how does, if we're thinking about transition paths between two fixed states,
yeah,
as opposed to just like sampling a really long trajectory and making sure that like the transitions, like it seems like either like I'm just having trouble fitting the transition path? Like why would you expect to look at a transition path and think that that would match up with the transition behavior of some really long MD trajectory,
Yeah.
which isn't like starting and ending at a fixed point. I could
Yeah.
totally just be
So
missing some background thing here. Apologies if
yeah.
so.
So a couple things. Wait, so I guess is your question like how do we sample the transition paths like from like how do you go from a Markov state model like a transition probability matrix to a transition path? Is that your question or is it something else?
Or it's kind of like my understanding is that there's this kind of um, from Hannes and Bowen's paper, there's this like transition matrix between your Markov state model modes.
Hmm.
Um, and you want to say that something that you guys are computing here like displays very similar statistics to those transition things. But the something that we've been discussing so far is just if I fix two start and end states,
Hmm.
like what do the paths between those look like? And it seems like the paths between two fixed states in general would look very different than just unconstrained MD over the whole
Yeah,
surface,
yeah, yeah.
which
Okay, for sure. Yeah, yeah, okay, I understand your
yeah.
question. So, yeah, no, to be more precise, the metrics that we're computing here, like what are we comparing against? It's not just long trajectories from not just like long equilibrium MD trajectories, but it's actually sampling, as they do in their paper as well, like sampling discrete transition paths from the Markov state model. So there's a way to like fix a
Oh,
start
I
state
see, I
and end
see.
state.
So they're also doing transition path sampling.
Yeah, yeah, yeah. So
I
they
see.
also
My
have
bad.
a part of their paper where they're doing TPS, and so yeah, it's like you fix a start state, you fix an end state, and you specify a trajectory length, and then there's a simple algorithm for sampling a transition path from the Markov state model, just based on like matrix exponentials and stuff. Where and so that becomes sort of the ground truth distribution, and then all the subsequent metrics are computed with respect to that. Yeah.
I see. Okay, that totally makes sense.
Yeah, yeah, yeah. But
My
you're
question has
absolutely
been
right.
answered.
Yeah, yeah. Okay, cool.
Thanks, Sanjeev.
Yeah. And so also, I mean, this is perhaps obvious, but we can do this a lot faster than like unbiased MD simulation. So those same sort of lengths of between like 1 microsecond and 100 microseconds, which were arguably in general like worse at capturing transition paths in general, also take like a lot longer, of course, because you're just doing unbiased MD. Whereas for us, we're like explicitly targeting the transition region. So we're much faster. But um, like to an MD person, this is probably like an uninformative slide because it's like, well, of course you're faster than unbiased MD. That's a very weak baseline, so that's for sure true. We also like for some of the other systems that we considered in our paper, we compared directly to sort of like traditional enhanced sampling baselines, things um, like uh Monte Carlo methods between or shooting methods between starting and end states is also like metadynamics and various things like that. Although that's harder to do those explicitly for these larger like proteins systems. So that's why we sort of had to resort to comparing to unbiased MD here. But check out the paper for also comparisons to things like sampling and metadynamics and things like that. Um, yeah, so some cool visualizations, like in general, sort of like we've these are sort of just like wiggling spaghetti balls that are a little bit uninformative to look at, but we do sort of a lot of energy analysis to make sure that we don't have sort of unphysical collisions and stuff happening, which sometimes do happen. So we sort of have some tricks to mitigate those as well. Also recommend that you look at the paper for those. One interesting thing we can do, as I mentioned, someone had asked a question about the delta t. So we can actually vary the delta t used in the OM action. And if we set it to be a very small value, and like we have a small time horizon versus we have set it to a large value and we have a large time horizon, we actually observe qualitatively different paths. So if we set a very small time horizon, you're basically saying, you're basically telling the model, you need to transition in a very short amount of time. So basically don't like spend time, don't waste time in any sort of like energy traps and just go as quickly as possible. Whereas if you specify sort of a larger time, you tell the model that, okay, like you can spend more time in these energy wells. Like for example, for this trip cage protein, this region of the phase space is sort of like a big energy minima. It's like close to the folded structure. And so if you allow a longer transition time, then the transition paths will sort of wiggle around a lot longer in these sort of energy traps before they go. And this is not, we're not retraining the model to do any of this. All we're doing is just re-optimizing the OM action with a different delta t parameter. That's a hyperparameter. That's the only thing that we're doing. So this is sort of a nice thing because at the end of the day, the transition path ensemble is conditioned on the time horizon that you specify. Like short transition paths are going to look different from long ones. So we can sort of capture all of these. And then, as promised, based on what Ezra asked, we can starve. We did an experiment where we sort of starve the model of like a lot of data in the transition regions. So specifically, what we did is based on the committer function here, which is sort of a measure of the progress along the transition coordinate. And we basically removed like all data that had committer values like anywhere not close to 0 or 1. And we sort of can see reasonable paths in some cases. I think for some proteins, it starts to break down, but for others, it's reasonably robust. So this is the I think, fundamental limitation where, of course, if your underlying data is not representing these regions well, then you're going to face some limitations. But this is where I would say coupling this with some access to the true energy function would be a promising approach. And then since we're running really low on time, I'll just wrap up by saying we also so far have not considered any sort of generalization. So in the talk so far, so now we also introduce sort of, again, very heavily inspired by Hans' paper. We actually used their data set of tetrapeptides that they used and sort of have a model trained on some tetrapeptides and then want to sort of generalize to new ones, to new sequences that have not been seen by the model, hoping that what we have seen is informative for what we haven't seen. And again, sort of we see by these metrics, good transition paths, but also by things like energy barriers and things like that. And lastly, we also show that you can compute like useful quantities like transition rates. So this is something that people are often very interested in, is actually computing like rates of transition, like binding on and unbinding rates and things like that. So there's a way to use our OM paths as sort of a starting point for an enhanced sampling method to compute reaction rates efficiently. So if you're interested in that, feel free to reach out to me or take a look at the paper as well. And so I'll just wrap up by saying that the key takeaways here are that we sort of introduce a method where we take models that are previously only thought to be good to generate IID samples and sort of repurpose them in a zero-shot fashion to produce actual transition paths. And we can use sort of the natural stochasticity of this generative process to obtain diversity. And we can sort of sample diverse paths with like different time horizons, different temperatures, just by sort of tweaking these parameters in the OM action. And so we can also enable zero-shot TPS on systems that we didn't see at test time. So this is sort of the idea that you don't have to sort of retrain for every system from scratch. And so there's some limitations, of course, just because of the fact that we're not exactly sampling from the posterior distribution. There are some approximations based on just the quality of the generative model. And so things that we're looking at in the future are like applying this to larger and more generalizable models like BioEmu and AlphaFold 3 and things like that. So in principle, our method should be sort of compatible with basically any good enough or like good model that's learned to reasonably sample like a distribution. And so we're also thinking about things like conditioning the transition paths on different cofactors or ligands and things like that. So if you're interested in any of these things or have ideas or have thoughts, it'd be great to discuss more. And so I'd really like to thank my wonderful collaborators on this project. And if you're going to be at ICML, it'd be great to chat. We'll be there. And then if you're interested in checking out the code or paper or any other details that I didn't have time to get to, that would be great. Yeah.
Awesome. Thank you so much, Sanjeev. I see we have a few questions. Do you have to Zoom right now or
Yeah, I have the Zoom.
maybe
Actually, I think
okay.
I see one question from Nivedita that I didn't get to. The application for sampling IDPs or short peptides. Yeah, so I'll preface this by saying I'm not like a expert on proteins. So like I know like intrinsically disordered proteins are like a big challenge and they're very difficult to sample and like model correctly. What I would say is that like if your training data or your generative model is good at sampling these IDPs, then this method should work on top of that. But I'll probably refrain from commenting too more since I'm not an expert on IDPs. But if you want to chat more about the specifics of that, feel free to reach out and I can at least point you to maybe the right direction. Yeah. Or understand your use case better. Yeah.
Okay, I see Ravi has a question too, but if there's no time, maybe there's like an email people can reach out to or something like that.
Oh, sorry, I didn't see that. But yeah,
It's
no, I'm
totally
happy
good.
to stick around and answer questions.
Can I ask
So
my
yeah,
question, please, or
yeah,
no?
yeah, go ahead. Yeah.
Yeah, thank you. Just a quick question, and then I'll let you be. I went through your paper. Thank you, Sanjeev. I really appreciate your presentation. I just want to ask a quick question. I went through your paper, and you said that I know that you said your advantage, one of the advantage was scalability. I know that I also noticed in your paper that one of your future research involves examining how pre-training generative models how on large structure-based databases enable TPS and unseen systems. So my quick question was, um, so what? I think I know you already said just now that what you'll try next is AlphaFold 3. So I just wanted to know, are you going to like try like other databases like PTBDB or Atlas and such, and will you be able to scale your models? That's the quick question I have. Thanks.
Yeah, no worries. Yeah, so I think the idea of scalability is really the idea that our method would benefit from scale of both model and data. So in the sense that as you have larger generative models trained on larger and more diverse data sets, like coming from MD or other sources, that this method, which is basically a repurposing of those models, will also improve. So a couple things you mentioned there, like AlphaFold 3 or like Atlas. So AlphaFold 3 is a model, and Atlas is a data set. So I guess in both those directions, we'd get to like model and data scaling. The issue with AlphaFold 3, as I know it for now, is although while it's a great model, it's really, I mean, and it does have like a diffusion model or a structured denoising module that's supposed to capture sort of a distribution of states, but it's nowhere near like actually capturing a full Boltzmann distribution of the sort of systems that it's modeling, just because it wasn't trained on like exhaustive MD data from that. So probably AlphaFold 3 would not be the like best starting point. Probably something more like BioEmu would be better because it's trained on more diverse data that's actually intended to sort of sample from these Boltzmann distributions. And then you mentioned like larger data sets like Atlas and stuff like that. Yeah, for sure. Those are data sets for which like if you I don't remember if BioEmu trains on that, but like again, yeah, if you had a model that was trained on that data, then definitely you could um, basically apply this method to those systems. So hopefully that clarifies what I meant by scalability and stuff like that. Yeah.
It does. Thanks, Sanjeev. Thanks.
Yep.
All
Uh,
right, any more lingering questions?
Yeah, I have a
Otherwise,
question,
okay.
but it must be stupid, but it would be better for me to, obviously I'm missing a lot, but I have this very shallow analogy with kind of reasoning in a latent space with whatever, large language models. It's very shallow. What do you think, like, where this analogy breaks, and would it be possible to kind of predict reasoning path or kind of sequence conversion path between point A and point B?
Yeah, that's really interesting. I someone mentioned this to me somewhere before as well, and I thought it was interesting. I'm totally not a language model expert or like a reasoning expert, but yeah, I think that could be interesting. I think like if you consider like the idea of like the starting point and the ending point being like the question and the answer of a model, and then like finding latent chains of reasoning between them. Yeah, at a very high hand wavy level, I think that kind of makes sense. But I yeah, I think that there could be something interesting there. I don't want to comment
Oh,
further and
yeah,
make a fool of myself. But yeah, we should chat more if you're interested in that. Yeah.
yeah, I'm interested. Okay, great. Thank you very much. Very
Yeah.
inspired talk, inspiring talk,
Thanks.
yes.
Alrighty. Sanjeev, thank you so much. This was
Thanks. Really
great.
appreciate it.
And thank you everybody else for coming.